Welcome back. We are now in the 33rd lecture and we are discussing the Runge-Kutta methods. So what we are going to do today is to discuss some higher order methods, and then from the next lecture we will discuss the errors of these higher order Runge-Kutta methods. So let me start sharing the slides for you. Okay, I hope that you are now able to see them, right? So let's recall quickly the Runge-Kutta method of order 2. There are more than one, but we are looking at the first one that we studied in the last lecture. So as usual, we have the initial value problem, dy by dt equal to f ty, a less equal t less equal b, y a equal to alpha. And this method that we have started with will describe the W naught, which is the first approximation, to be alpha. And the next ones onwards would be Wi plus 1 equal to Wi plus h f ti plus h by 2, comma Wi plus h by 2 f ti Wi. So this is what we have in the first Runge-Kutta method of order 2. Normally, you should notice that whenever you have a nested evaluation of the function value, so when you have the first f here and then there is another f inside that, this typically refers to the derivative value. So what this has is that it's going to give you the derivative, meaning of course you remember the computation of the derivative that we have taken. So this does refer to f prime or y double prime. Okay, so the nested evaluation of the function values depends on how many derivatives we are looking at of the function f. All right, so that is what we have. Normally what would happen is that the t value will change by the step size, so there will be an h factor, a multiple of that, whereas the y value or the wi value will change by the function. So you may sometimes even have this inside ti wi being changed by ti plus some factor of h plus comma wi plus a factor of h times yet another function value. So this is what will normally keep happening in the higher orders. So this method, as you remember, was obtained by equating the capital T of t comma y, which you remember was f of t comma y plus h by 2 f prime of t comma y. And we equated this with a1 t plus alpha 1 comma y plus beta 1, and then we solved for a1 alpha 1 and beta 1. So there were three parameters which were involved in this, a1, alpha 1 and beta 1, and they were all needed to get the match with capital T. So if you are looking for a higher order Taylor method, if you want to use a higher order Taylor method, where would you use a higher order Taylor method? You will use it to compute this function value. We will use a higher order Taylor theorem to compute this value, and then we would equate with a higher order, possibly higher order capital T. Then you should have a more complicated form than the one that we have highlighted just now. Okay, so that is necessary because with three values, this is the best that we can do. We cannot do anything better than this. So let's say that we are now looking at this. We are changing the form by looking at a1 function value plus a2 function value, and then there is one more function value inside. So this is again of the similar form. You are looking at the second derivative of the function y or the derivative of the function f. Okay, that is what we are looking at. So we have four parameters, and what we would try to approximate with this is this slightly complicated capital T, which is f of t comma y h by 2 f prime t comma y, and now we are adding the f double prime t comma y. So by the analogy of the nested function evaluations that I gave you, what we have seen is that our form has only one nested evaluation, and therefore it should refer to f prime. This f double prime should somehow be slightly more complicated than the form that we are using. And indeed that happens. When we try to equate these two things, then there is an insufficient flexibility to match this particular term, which results from the expansion of the double derivative. So there is no way we can compute and equate this particular one. So this is the h square by 2. If we could also have determined the h square by 6 thing, then our order of the error would have been h cube. But that is not possible. So consequently, the best that can be obtained from this particular 4 parameter form, these are methods with big O of h square local truncation error. You cannot go beyond h square. So this is something that we will have to ignore, and we will again look at the old capital T that we had seen. In fact, it is very common to put the order of the capital T here at the superscript of capital T, but I have done it to I have not put it to simplify the notations. Okay, so we are going to again ignore the h square by 6 term, put capital T comma y equal to f of t comma y plus h by 2 f prime t comma y. That's the t that we are going to look, and we will keep this bigger or slightly complicated form of the 4 parameters. Okay, and now if you remember the one which we had used for the earlier one, which gave us the midpoint method, what it said was that, we had 3 parameters and they were sufficient to match the two things. Now we have an extra parameter, and so we have some flexibility. So that flexibility will allow us to get a number of big O h square methods. You can put various relations between them and obtain more and different methods. So one of the most important ones in them is called the modified Euler method. So this particular method refers to A1 equal to A2 equal to 1 by 2 and alpha 2 equal to delta 2 equal to H. So let's see where the difference equation has these A1, A2. The A1 was coefficients for this F, Ti, Wi. So that 1 by 2 has come out with H, and we get H by 2. Similarly, A2 was the coefficient for the second F value, and that has also come as 1 by 2 outside. Okay. The alpha 2 being H said that Ti plus alpha 2, but Ti plus H. H is the step size, and if you add it to Ti, you go to the next node, Ti plus 1. That is what we have obtained here. And then delta 2 being H means that here we would have the constant, the coefficient H for the inside one. Okay. So this is the difference method that we have for this modified Euler method, and this differs very slightly from the Euler method, as you will notice, and therefore the name is modified Euler method. Okay, I told you that when you have nested interval, for Euler method, our function was the capital T was simply the f, and here we have modified it by some slight change, and therefore this is called the modified Euler method. Let's do an example as we have always been doing. It's the same example that we are looking at. Our usual example, which is y prime equal to y minus t square plus 1, 0 less equal t less equal to, y of 0 is 0.5. We take capital N to be 10. So our h will be 0.2, Ti will be 0.2 into I, and W naught has to be 0.5 because you are looking at the initial value to be 0.5. Then what we will have is that W naught will be 0.5 and Wi plus 1, I am just going to give you the final form now, will be of this form: Wi plus 1.22 Wi minus 0.0088 I square minus 0.008 I plus 0.216. This is for I equal to 0 to 9. And the first two approximations that will happen will be that W1 is 0.826 and W2 is 1.20692. So the table is this. So we see that I have put here the midpoint method, and the modified Euler method, and we observe that the errors for the midpoint method where the maximum error is 0.0151025, whereas the error for the modified Euler method is 0.0724173. So the error is slightly worse in the modified Euler method. Although we have 4 parameters, but we are putting the values for those four parameters, or we are putting some relations between them, and therefore we are getting the modified Euler method, but the errors are somewhat bigger than the error that you would obtain for the midpoint method. But we are going to see better and better methods. We are actually going towards better and better method. If you notice, the point for midpoint Euler method was that there were two values involved. So you had f of a1 f of t comma y plus a2 f of something something. So that is the thing that perhaps we should try to avoid. So what we now do is that we try to approximate this third form of capital T by this complicated form. So here I have a 4-parameter form. Once again, I have alpha 1, delta 1, alpha 2, and delta 2. You know, our convention is that whenever we are putting a constant outside the function value right in the beginning, we denoted by a1, a2, and so on. When we are putting it inside, but it's being added to the value of t, then we call it alpha 1, alpha 2, and so on. And if you are putting it within the function value, but as a coefficient of function value, then we call it delta 1 and delta 2. Okay, if you were adding a simple constant to the y term, that would be called as beta 1, beta 2. Okay, so those are the conventions that we are following. So here you notice once again, here we have an f. Okay, so there is an fty which is inside this delta 1 of fty, which is inside the further f. So there are 3 nested evaluations of f, and so it should reflect that we are looking at f double prime. So now it is worthwhile looking at this particular form matching with capital Ty as we have given here, corresponding to the second derivative of f. And now we can hope that if you can match with the capital T involving f double prime, then the error will be of the form of the order of h cube. So this can be done, of course, and the derivation of all these constants is a bit involved, but what we will just do is that we will tell you the final answer. The method is called Heinrichs method. This is yet another German mathematician working in this area, this part of numerical analysis. And the different equation of Heinrichs method is given exactly in this form. So we see that your alpha 1, delta 1, alpha 2, delta 2 can be computed depending on the values of h. Okay, so let's try to apply it to our usual example with the same values of capital N, and the difference equation then turns out to be this. So there are so outside you had h by 4, and then there was inside some 2h by 3 or h by 3 and so on. So this 1.3 bar reflects 1.333333, 4 by 3 actually, and this 0.06 bar, this represents 2 by 3. So this is how the difference method for difference equation for Heinrichs method looks like. And the first two values, as we compute them always, are 0.829244, 1.2139750. And the table, now we see that the errors are much better compared to the errors that we had obtained in the midpoint method and the modified Euler method. So both the method of order 2 were worse than Heinrichs method, which is the method of order 3, because it's giving you the error in the order of h cube. Okay, so this method is definitely superior to the method that we have seen earlier. Now there is the Runge-Kutta method of order 4, and this is the most common Runge-Kutta method. The one of order 1, the one of order 2, and the one of order 3, they are not the common methods, but this is the most common, and we will see towards the end of this lecture why this method is the most common method, why this is the method which is often used. And this method, of course, you will have several nested evaluations, but they are being taken care of by writing the function by introducing this k1, k2, k3, k4. Okay, this is what we are doing, where k1, the first one here, this is the function h times f of ti wi. K2 is h times f ti plus h by 2 and wi plus 1 by 2 k1. So k1 already involves a function value. All right, so k2 is something which is f prime, because it is a nested evaluation of f within f. K3 will involve K2 here. K2 is already something which involves, which corresponds to f prime. Since this is within the function evaluation for h, for f, K3 corresponds to f double prime, because there are three nested evaluations which are happening. And then K4 will correspond to f triple prime, which will have coefficient h cube by 24. And so we hope that the error, if you are able to compute these coefficients nicely, then what will happen is that the error will be of the order of h power 4. Okay, so this K1, K2, K3, K4 are defined in this way, and this particular method has local truncation error big O of h power 4. And therefore the order of this method is 4. What we will need is that yt should have 5 continuous derivatives, or f should have 4 continuous derivatives, because we will need to talk about the error also. Okay, the notations k1, k2, k3, k4, as I told you, they are introduced to eliminate the need for successive nesting of the second derivative of the function evaluation. So to not have to deal with those nestings, we are introducing these k1, k2, k3, k4, and they can be computed very nicely. So in particular, for our example, when we take capital N equal to 10, h equal to 0.2 and ti to be 0.2 times I, the k1, k2, k3, k4 can be easily computed. K1 is 0.2 f of 0, 0.5, which is 0.2, 1.5. You will take the function value here and evaluate it at that, and this is 0.3. K2 is the next evaluated nested interval. This is 0. Nested function evaluation. This is 0.328. K3 is 0.3308 and K4 is 0.35816. And now the difference method is going to be correspondingly, and then the first computation that we can compute will tell you that the W1 is 0.8292933. And as usual, whenever we do this thing, the table has to come, and the table you see is superior, is far better even than the Heinrichs method. This is of course expected, because our errors are of the higher order of h. And this is something that is expected anyway. So almost up to first 4 decimal points after the 0, we have the same values throughout our interval 0 to 2. Okay, so we have seen several such methods, and now there is a time to compare these methods from the computational point of view. But before we go towards the computational point of view, I may ask and answer the question as to why do we stop at 4? I said that this Runge-Kutta method of order 4, this is the most common method. So why don't we go to order 5 or order 6? Of course, there may be some computational difficulties. So we would want to know why we don't do that. And why do we not do the Heinrichs method, which is of order 3, or the other methods which are of order 2? Because they will be computationally simpler. You may actually be using smaller step size for them and get a better approximation than using the method of order 4. So why don't we do that? That is something that we are going to answer now. So let's just, the very basic thing about Runge-Kutta methods is that you have to evaluate the function, and there will be some nested evaluations. Okay. So in the second order methods, the local truncation error that you get is of the order of h square, whereas the evaluations are two function evaluations per step. The Runge-Kutta method of order 4 requires 4 evaluations per step. So you have to evaluate K1, which is once, K2, which is second time, K3, which is third time, and K4, which is the fourth time you have to evaluate the function value. So there are 4 evaluations which are required, and the local truncation error is also big O of h power 4. Okay. So we are actually going to give a table which a very brilliant mathematician has obtained, and he has compared the number of steps, which are the number of evaluations which are required for the Runge-Kutta methods of various orders, and the best possible error that we can get for them. So the table will have evaluations per step, the function evaluations, and the best possible local truncation error. Okay, this is the thing that we are going to compare. And we have seen that when there are two evaluations, we have a method whose local truncation error is big O of h square. Okay, so there are actually two. We have the midpoint method and we have the modified Euler method. Both of them have the local truncation error to be big O of h square. Then Heinrichs method says that when you are allowed to have 3 evaluations per step, then there is a method whose local truncation error is big O of h cube, and it cannot do more than that because you cannot equate. For instance, for the evaluations per step being equal to 2, we were not able to compute all the coefficients if you were looking at a complicated capital T, right? And for 4, we have the Runge-Kutta method of order 4, whose truncation error is big O of h power 4. But now comes a twist. If you take any of these Runge-Kutta method of order n, where n is 5, 6, or 7, you don't get the local truncation error to the order of h power n. It is to the order of h power n minus 1. Which means that you cannot equate that capital T with a form having n parameters where n is 5, 6, or 7. You have to go to the smaller t by one size, and that you can equate. So this is what happens when you have 5, 6, 7. If you are looking at 8 and 9, in fact the n even drops by 1. For 8 and 9, the order of the error for a best possible method that you can get is big O of h power n minus 2. So actually, to think about this, if you were looking at the method which uses only 5 evaluations per step, that is same thing as looking at method which uses 4 evaluations per step, because for 5, we are going to get the order of the error to the h power 4 only. We will not get it to the h power 5. And similarly, by the same argument, the method which uses 8 evaluations is similar to the method which uses 7 evaluations. And this becomes even worse when you go to the next level. If 10 or higher, then the error is the maximum, the best possible local truncation error that you get is big O of h power n minus 3. So we see that somewhere 4 is the best thing that you can have, because for 4 you get the best possible error, which is the big O of h power 4 to the order of h power 4. And even if you add things to 4, if you go higher, then you are not getting the required error going again higher. And this is why methods of order less than 5, but with smaller step size, they are used in preference to the higher order methods using a larger step size. Okay, so this is why this explains why we said that the Runge-Kutta methods of order 4 are the most commonly used methods. There is one more way to compare various methods, and we do it now. So this is what it does. The Runge-Kutta method, because you have 4 evaluations, because there are 4 nested evaluations, so there are 4 evaluations that you have to do per step. Whereas Euler's method will require only 1 evaluation. And if you want to claim that Runge-Kutta method of order 4 is to be superior, it should give more accurate answers than Euler's method with 1/4 of the step size. So what are we looking at? We are looking at the Euler method, which has say step size h, and we will compare it not with the Runge-Kutta method with the same step size. That would be incorrect, because Runge-Kutta method needs more function evaluations, whereas Euler's method requires only a single evaluation. So the comparison is not fair, because even though the Runge-Kutta method might give a better answer, somebody may argue that you are going to use 4 evaluations for Runge-Kutta method, so it's not that good a method. So we will say that, okay, fine, we will reduce the step size for Euler method. So to reach, let's say, the 4h step size, the Euler method will require 4 steps, because it will go from 0 to h, then 2h, then 3h, and then 4h. So going from 0 to h will be one function evaluation, going to 2h will be second, 3h will be third, and 4h will be fourth. So now there are 4 function evaluations for Euler's method. And Runge-Kutta method, we are using the step size to be 4h. So it is just one step. And in that one step, we are using 4 evaluations anyway. And then we compare the errors. Okay, that's what we will do. But in between, let's also push the method of order 2. So if it is supposed to be better than second order Runge-Kutta method, then we again apply the similar logic, which will be that for the step size h for Runge-Kutta of order 4, the second order method with step size h by 2 should be compared. Okay, so if we compare all these three, Euler's method requires 1 evaluation per step. The second order method requires 2 evaluations per step, and Runge-Kutta requires 4 evaluations per step. So if we say that our step size for Runge-Kutta is a particular step size, then we will take half of that step size for the second order Runge-Kutta method, and half of that, or 1/4 of the original of the Runge-Kutta of order 4 step size for Euler's method, and then we compare all these 3 methods. That would be the correct comparison. So this is what we will do, and even then the Runge-Kutta of order 4 will be still superior, and this explains why this is the most commonly used method. So we will use our same problem, initial value problem. The Euler's method is for 0.025. Midpoint method, which was better than the modified Euler method, midpoint method is for 0.05, which is twice the step size of the Euler's method, and Runge-Kutta fourth order with step size 0.1. Okay, now we are all right, and we will compare these methods at common mesh points, the 0.1, 0.2, 0.3, 0.4, and 0.5. These are the 5 nodes at which we will compare the functions approximations given by these 3 methods. The evaluations required for each of these techniques are 20. Correct? Because for Runge-Kutta of order 4, there are 5 steps, and each step requires 4 evaluations. So there are 20 evaluations for Runge-Kutta. The midpoint method at each step will require 2 evaluations, but since it is 0.05, it's going to take 10 steps to reach 0.5. So again, there are 20. And similar with Euler's method with h equal to 0.025, it will require 20 steps, but there is only one function evaluation at each step. So there are in all 20 evaluations. Okay, so let's see the table. We will see that the fourth order method is clearly superior. Here is the table. The exact values are noted here in the first column, and the Euler method, we see that already for the 0.1 you have gone slightly away. Instead of 6.6574, it is 6554. Modified Euler, I am sorry, I think this is not really the midpoint method, but it's taking modified Euler method. I am sorry, I should change the wording from the earlier slide. So the modified Euler is taking 6573 instead of 6574. But we see that Runge-Kutta of order 4 is correct to the first 6 decimal digits. So, and if you go all the way up to 0.5, we see that Runge-Kutta is correct for first 5 decimal digit, 42563. Here we have 42563, whereas the Euler method is correct only up to the first digit, and the modified Euler method is correct only for the first 3 digits. So this says that our Runge-Kutta of order 4 is superior compared to all the other methods, and I have given you 2 reasons why this is the best method. Number 1 reason is that as you go from the methods of order 2 to 3 and to 4, the errors increase and they are respectively of order h square, h cube and h power 4. But beyond that, you don't get the if you are using n evaluations beyond 5 onwards, you don't get the error to be of the order of h power n. So you may actually end up spending more time doing the evaluations, but you don't get that much error order, and therefore the n equal to 4 seems to be the optimum. But even when we compare it with the methods of order 1 and 2, by taking the number of function evaluations, even then we see that our method is much superior. So we stop at this moment, and in the next lecture we will be discussing the errors that occur in these various Runge-Kutta methods, and then we will see where we go after that. So thank you and see you in the next lecture.